Welcome everyone to the second seminar in the Tech and Medicine series. I'm Jaeyoung Kang. So I'm a senior in chemistry. But all my research is mostly in like clinical sciences, and particularly I'm interested in the analysis of clinical data to better improve treatments for conditions that are related to brain injury. So today I just want to share a little bit about the kind of research that I've been doing. I just also wanted to show you a little bit about how machine learning is helping doctors currently in the neurocritical care unit. So, yeah. Oh yeah, and again, like just like last time, so this is like super informal. So you guys can like chime in with questions, and leave comments in the chat. The goal of this like isn't really I think like the technical details, but just to like get you guys introduced to the kind of research that's going on, and maybe give you some ideas for things you might want to do in the future. All right, so let me share the screen. Okay, can everyone see this? Okay, good. Okay, good. All right, so recently I got into machine learning for the neurocritical care unit. So right now I work in the lab with Dr. Jefferson Chen, and Dr. Jefferson Chen is a neurosurgeon in Caltech as well, and he currently works in the UC Irvine Medical Center. So when he brings in a patient to treat their traumatic brain injury, or just this can also apply to any condition that exhibits like a similar symptoms for brain injury. So like stroke patients, right, also can exhibit hemorrhaging in the brain. So any kind of like brain injury case, Dr. Chen gets a lot of data from like monitoring those patients, and he really wanted to use that data to try to develop some better way for diagnosing the patients or assessing how their overall improvement is going. So that's where I was brought in, right, to work with that kind of data. But the thing is, this kind of data tends to be super complicated. And this is kind of like the problem of data analysis, especially for like a doctor. So in general, like doctors aren't like super familiar with like computers or like math, like the way, for example, like a CS major is, right? And TBH, I'm not too like at that level yet either, right? Probably never will be, but but anyway, like, and so basically, we're not like that. The medical field isn't super caught up on those kind of techniques yet, and yet when we're given this kind of data, like we have to figure out a way to analyze it, right? This is just a sample of the kind of data that neurosurgeons have to kind of work with when they're monitoring patients. As you can see, there's a lot going on. Like there are a lot of different parameters or variables that they're measuring. I guess like this is a very clean set of data because you can see that there are some trends here, like denoted by the arrows. But in general, like most of the time, like you're not going to get a data set that's like this clean, right? So the problem lies with how are we supposed to like get this to work, because we want to use this to assess a patient going forward. So as you can see, there are a lot of parameters, and this kind of adds to the overall complication of the problem. And the reason why there are so many parameters is because doctors, especially for treating brain injury patients, like to put them through a process known as multimodal monitoring, which essentially means that if you have a brain injury patient, you're going to be monitoring many different parameters at once and getting like an overall assessment of like the patient's well-being, not just in one area, but in many areas at once. So right now, this is a picture of a patient with cerebral edema. So cerebral edema is kind of like the condition that like unifies a lot of like brain injury examples. Like, so whether you have like a traumatic brain injury case from like getting hit on the head, for example, or like you have some kind of brain injury or hemorrhage resulting from a stroke, like it's pretty likely that you might have like cerebral edema. And cerebral edema basically just means that your brain is like swelling. So you can see like the swelling, yeah, in these pictures. Actually, in the second picture, you can see like the black ring around that white circle is getting a little bit bigger. So that swelling or brain bleed is getting a lot bigger. But yeah, when you have a patient like this, you're going to be monitoring them through, oh crap, sorry. Yeah, you're going to be monitoring them through various different means. Yeah, and you'll be seeing, a lot of these kinds of analyses being done. There are more analyses besides the ones that are pictured here, but this is just like a good example of the kind of things that doctors will have their patients be put through. So yeah, because you put them through so many tests and try to get a picture from so many variables, like you're going to get a lot of data that's like complicated like this. And that just kind of adds to the overall issue that like doctors have with trying to analyze a data set and trying to get out some patterns that they can work with. Yeah. So this is where doctors have tried to turn to machine learning and statistical approaches, right? So I have to emphasize that like these kinds of machine learning and statistical approaches, like they don't necessarily need like you don't necessarily need like a ton of, I would say, like programming experience to like at least get started, because there are plenty of packages that you can use from like open source software where you can kind of like feed in your data and it'll like give you back the things you need. Yeah. So if you read the literature on neurosurgery, like there have been plenty of methods that have been used in the past. I just like gave like a general list here. Yeah. So each method is slightly different and is pretty different and has a lot of like complex like nuances for the methods. Yeah. For our purpose, like we just have to know that like that doctors have tried a lot of different things in the past, right? And you can find examples of these throughout the literature. Yeah. So anyway, so I was brought to the Chen lab. Yeah. So I was given this I was basically just handed a set of like multimodal data, similar to the chart that you saw, except for our data set was like a little bit small, so maybe like 10 to 12 patients. But anyway, I was handed that kind of data set for those patients. And you have to keep in mind that each patient is going to have at least like somewhere between like 100 and 200 data points, because we were measuring hour by hour. Yeah. So the issue is that like most of these methods previously that have been previously used by neurosurgeons were mostly used for classification, and specifically the classification of mortality. So what that would mean is that that you would feed the patient's data through these kinds of methods, and then the idea is that you would try to use that to design a model that will predict whether the patient will live or pass away. Yeah, but for what Dr. Chen wanted, he wanted a way to assess the patient just a little bit into the future. So essentially, he wants a model that can do some kind of regression prediction and not a classification prediction. Yeah, so that was where we were at, and this kind of regression. Yeah.
What's the difference between like kind of classification and regression and things like that?
Yeah. So I think the way I like to think of this, I think the way I like to think of this is just actually this example is a good example. So let's say you're given a set of data for a patient. Let's say you take the measurements hour by hour, and let's say you took those measurements over 3 days. So if you wanted to classify, for this example, you would want to, for the case of a doctor, the thing that's really important is predicting whether that patient is going to live or pass away. So essentially, classification problems result in binary outcomes. However, in the example that I said here, Dr. Chen wants a regression model that can predict the measurement for an hour for a certain point of time, and that kind of measurement is not going to be a binary outcome, right? Like that measurement, like especially if you're measuring, like for example, like a glucose level or a lactate level, like that could be like any number. So a regression outcome is the outcome is not binary, and the outcome is like it could be any number. So I think that's like it's kind of like a rough definition, I think, for the difference between like a classification and a regression problem, right? So the classification problem is going to have a binary outcome, and the regression analysis, the outcome is not binary.
Gotcha. And then the regression one's harder to do, I'm guessing, right?
Yeah.
Okay.
Yeah. Doctors in the past have tried have tried doing regression models for this kind of data, and they haven't had that much success yet. Although they did have quite a few successes with the classification of mortality. Yeah, so that was where that was where we were. We essentially had to come up with a regression model, even though this kind of thing hasn't really worked before. So it turns out that there is one kind of approach that doctors haven't really tried yet, and that's gradient boosting. So I listed boosting here. Listed boosting here as one of the things that doctors have tried. Yeah. Yeah, but like gradient boosting is like kind of like a flavor. It's like a flavor of boosting, and I just said that kind of thing hasn't really been explored yet. So our lab decided to try that. Yeah, so we just found an R package that can do that. And R is like a standard statistical and machine learning software that like many people use for these kinds of analyses. Yeah, so gradient boosting techniques, as I said, like it's a specific flavor of boosting that hasn't been well represented in the literature yet. And I think maybe going forward, people will try to do this more, but as of right now, it's not very well represented yet. Yeah, so I kind of listed the algorithms here, and these algorithms are like, the math behind it is like pretty complicated. But basically the way I like to think of it is like, I'm sure like many of you have taken algebra, and you guys understand, and you guys have learned about like if you have a set of data, right, you draw a line line of best fit that captures that data, right? So essentially the way gradient boosting works is that you're going to have a set of data, and you're going to draw the line, right, that captures that set of data, and that line is going to have an equation associated with it. However, you can then modify that line by adding something to that equation. So let's say like fmx equals fm minus 1. Fm minus 1x was the original equation. You would add a weak learner hmx, right, to modify that line a little bit. Then you would repeat the process and add it again, add another hmx, and essentially you essentially keep like shifting the line a little bit this way and that way until you get something that captures the data more accurately to the level that you want. Yeah, and so every time you change the line by adding an HMX, that would be like an iteration. Yeah. So basically, like how you what you do to the weak learners every time you add them is essentially basically is kind of like the flavors that you can do for gradient boosting. Friedman's gradient boosting algorithm is the one that this particular package uses. Yeah. Again, like the technical details aren't, I think, too important, except for the basic idea that you have to you keep modifying the equation by adding some kind of weak learner. Yeah. So yeah, and so once we decided what we were going to do, we have to actually do it. Yeah. So the process for a project, and this is kind of like the process that many pretty much machine learning is this is how machine learning pretty much goes. So you get a data set and you have to prepare it. In our case, preparing would essentially just mean looking through the data, seeing if there are any points that are, for example, we think would be wildly inaccurate, or could be a result of an error from a measurement, and we would need to take that out. The criteria for this is it would be best seen by a doctor. I think in our lab, Dr. Chen went through this before he handed me the data set. Yeah, but essentially the way this would work is usually our errors would end up being would be a measurement that's too high, and we know that that's we would know that that's a error of the machine's measurement, or the multimodal monitoring measurement, because we know from from medicine and biology that if you see a measurement that high, the patient is pretty much going to be passing away very, very soon. But if that patient ended up surviving or doing really well, we would know that that's probably not an accurate measurement, and we need to throw that out. Yeah, but basically we have to go through our data set, and we have to kind of go through this process of just polishing it. Yeah, because machine learning, a large part of machine learning is statistics, and as you guys know from statistics, when you do a project in statistics, that project can only be as good as the quality of your data set. So that's that's definitely a huge part of the process, just going through the data set, just looking it over again and again, taking out the errors, if you can get more, samples, add them in, things like that. Yeah. So once we do that, then we can create our model. Yeah. So we'll split the data set and then we'll design the model on the training set. So the concept of training set and testing set is pretty important in machine learning. But basically what that means is just if you have like a data set, in our case, our data set was like 12 patients. So let's say you have like 12 patients, right? And since we were taking data hour by hour, we would have about, we ended up having about like 1,200, 1,300 data points. Yeah, so we have to design our model on a certain number of those data points. So it's like, if you were thinking about just like, drawing like a standard, like, XY line, you need like a certain number of XY coordinates that you can use to like make your line. So that split. So once you split your data set, you design that line. Well, I guess in this case, like I'm skeptical about it. It's like it's not really a line, but like you get the idea that you make your equation on a certain number of the points available, and then you use that equation that you made, and then see if it predicts the data that you set aside really well. So the data that you set aside would be the test set. So you test the model on the test set. Yeah. And another big subtlety of machine learning, which I guess our particular project didn't get into, was the way you split your set. Yeah, I mean, for example, let's say you have like, again, with our example of 12 patients, you could split, you can split by like, for example, making your model on 11 patients and then test it on one patient, and then try redesigning the model again on like a set of 11 patients that's like different than your previous set, and then test it on like the patient that's left, and just keep repeating the process so that you end up testing variations of the model on like every single patient, right? So that's like one way to do it. Yeah, there are many variations on splitting, which is another subtlety of machine learning. But for now, we wanted to keep it simple, so we just randomly sampled our set of patients. We chose a test set from that random sample, and we set it aside, and then we just tested, and we just designed our model on the patients that were left. Yeah. So yeah, so the thing is, now we have to actually assess the results. Again, then this is the part where get into statistics. In general, especially this is like a regression problem. The important thing is to make sure that like your measurements are actually, the measurements that you predict are somewhat close to the measurements that you actually see in real life. So that's where we use things like root mean squared error and mean absolute error. Yeah. So as you can see, there's a root mean squared error and a standardized root mean squared error. Like these two are like pretty much the same thing. It's just that the standardized root mean squared error, it was standardized by dividing by the standard deviation of the training set. Yeah. But if you want the actual error, you can just look at this RMSE value. And then the mean absolute error. Yeah, so the root mean squared error is calculated through like a somewhat complicated equation, but the mean absolute error is like another very, very simple way to assess how accurate your predictions are compared to the actual measurements. And this is essentially you just get a subtraction of the predicted and observed for every single point, and then just like average them out, right? And then just like make sure you take like the absolute value. Yeah, I think our error ended up okay because our overall like set, the means tend to hang around like 50 or 60. So that means like our mean absolute error is it's going to be off, based on the mean absolute error and the root mean squared error. Our data points are usually going to be either like 6 or 7 units off. Yeah, we were predicting the LP ratio, and for in the literature, like that kind of like standard is like okay. Yeah, and I think oh yeah, Michael.
What is the graph on the left saying? Sorry, I don't understand.
I was about to get to that. So yeah, I was about to get to it. So I said So I said that the iterations, that every time you like adjust the model, you add like a weak learner, right? And like that'll like kind of shift the graph a little bit. And that one time where you adjust the model that way is like an iteration, right? So what this graph is showing how the error tends to change with the number of iterations. So you see that like on the y-axis, this says outer sample standardized root mean squared error, which is what we have here. So what this is showing is that like every time like the model adjusted and predicted the values, you would like let's say you only adjusted the model once, like the error, the root mean squared error would be somewhere around like be somewhere around like 0.34. Yeah, and then like as you adjust the number of iterations, this error is going to go down. Oh crap! Yeah, I'm gonna get to that in a second. Yeah, that error is going to go down. So the important thing to remember is that like just because you increase the number of iterations, like the number of times you like add a weak learner, or basically every time you like move the model like around a little bit, that's not going to necessarily make your model more accurate. So you can't like so essentially it's not like this is going to keep going down because you like as you go up increase the number of iterations. If that was the case, we would have done like 1,000 iterations, for example, or just like however many iterations that are required that you can do like without like crashing your computer. Yeah. So part of the reason that we don't like we don't increase the number of iterations like endlessly is because of the idea that you can like overfit your set. Essentially, like your model predicts like the points in your overall data set really well. But then as soon as you try to use that for like points that are outside of your data set, like it doesn't really work. Yeah. So that's like one example of like what can happen, which is why you don't want to like increase the number of iterations too much. Yeah. The other thing is like, sometimes like, yeah, the models, like even if you just increase like the iterations, for example, to like 50, like it is possible that the error of the model will just like, it'll just go up. Yeah. So we definitely had to like, try this like training testing procedure several times to make sure that like, we could get to like the ideal number of iterations. Yeah, sure. Yeah, I'm sure there's a way to like formally calculate this, but within the field of medicine, like I said, like people aren't too familiar with this, and TPH neither am I. So we have to just find the iterations by running them, by just like running this whole procedure like over and over again. Yeah. So so trial and error essentially to find the ideal number of iterations. Wait, Michael, did that answer your question?
Yeah, that's super helpful. Thanks.
Oh, okay. Yeah. Okay. So anyway, so we found the ideal number of iterations, and we managed to like minimize our error. And if you see how the predicted measurements and the observed measurements look like we have a graph here that kind of shows it. So we predicted, it doesn't really matter like what kind of variable like you predict, because like that's essentially like you would use the same process. In our case, we just predicted the LP ratio because it's well agreed in the field of neurosurgery that the LP ratio, or the lactate pyruvate ratio, is a good measurement of patient illness. So we decided to just like go with trying to predict the LP ratio for now. Yeah, so as you can see, like this is the predicted curve in orange, and then this is the observed curve in blue. So this is kind of like where like you see like maybe like there are some limitations with the model, right? I think if you just look at this, like the model kind of captures like, I guess maybe like the big picture of like where this patient is going like well enough, I guess. But there are some points where like the model is going to be really crap for predicting a specific value, right? You can kind of see this like in the middle, right? Hours maybe like 40 through like 80, right? Like you can kind of see that like there's a point where like it's spiking, and where the measurements are spiking and the model just can't capture that. So the reason we saw this kind of trend in a lot of our predicted patients, but the reason why this model still ended up like the error still ended up okay was because the errors at the beginning and the end were pretty low, which is a subtle point, that you have to kind of think about when you're trying to make a model for prediction. You have to see how your error is distributed. Yeah. Even so, this is still valuable, even if you can't like predict like every single value completely accurately, because even having the general idea of like a trend is pretty valuable. So like, if you know that a patient is going to be staying in the hospital for a certain number of days, just knowing where that patient is going to be at the very end, right, that could be valuable. Yeah. And also we have to keep in mind that our sample size is pretty low from the beginning. So like, it's just that the more samples you add to the set, like the model will get better and better at capturing things like this. So this is more like so I would say this really is more like a limitation of what we were given rather than the actual procedure itself. Yeah. We're working with people, so we can't get new samples really, really quickly. Yeah, we can't give people brain injuries. Yeah. Yeah. So as I mentioned, the main limitation is a small sample size. Yeah, and that'll result in like the kind of trends that you saw there, where like the model is kind of crap at predicting certain values. Yeah, and related to that, the error distribution isn't like uniform longitudinally. So it's good at predicting the start and end, but isn't good at predicting the middle. Yeah, and also again, as you've learned in statistics, like kind of like the kinds of variables that you have to consider like are going to matter for your analysis. For example, if you were making a model for predicting the election, right? But like you didn't take into consideration like important factors such as like geography or like demographics, like you're going to like your model for predicting like the election is not going to be that great. And the similar and so like your model's accuracy will only go up as you add in better variables, more and more variables for prediction, more relevant variables. So in our case, the relevant variable that we couldn't add because the hospital didn't have the data for it at the time was the data regarding these post-operative life-sustaining procedures. Basically, what that means is after you do an operation, the patient is going to require certain interventions in order to keep them healthy. So a good example would be like intravenous injections or intravenous administration of like saline solutions. And so we couldn't consider that in our model. The hospital didn't keep a record of it. We would have definitely considered if we had that data. And similarly, another thing that we couldn't consider was the zone of edema, which basically means if a patient is like injured in the head and they get like a brain bleed, because like the way we measure the data is by essentially sticking a probe into the area and then like kind of taking measurements with that probe. Like depending on how close or how far away the probe is, like the measurements that you get are going to be a lot different. If you put a sensor in like right next to the bleed, the measurements are going to spike. But if you draw it out and kind of keep a distance from it, like the measurements are going to not going to be as like high on average. Yeah, so this kind of like location is kind of important. Yeah, and so we asked. We're right now we're at the stage where we asked the hospital to give us like the CT scans for all our patients, so that we can kind of like use coordinates to assess where the measurements were taken relative to the bleed. Yeah, So I think besides the things I've touched on, if there's anything else I want to say for like the future directions, we would mostly just try to make like a similar model for other conditions that are related to brain injury. So with our example of like people who develop cerebral edema, they can develop long-term chronic conditions such as hydrocephalus, and that's definitely something that would be interesting for a machine learning approach. Yeah. Also, like comparing the things that we do to other like statistical methods is definitely valuable. As of right now, like we found that our model is more accurate than regression attempts made by like other doctors with other kinds of procedures. Yeah, but just comparing that, continuously pairing it as we go into the future is more helpful. Yeah, and this idea of like trying to hold out and cross validation over holdout. This is a essentially this is kind of what I was talking about with like how you split your set. So it's like a subtle, so just like trying to split our set differently instead of just using the same split every time. So yeah, splitting is definitely the way you split is definitely something you have to consider. Yeah, but I think this is like of all like the rest of these are like it's like we can cover it more or less. But this is like probably the biggest limiting factor, I'd say. The idea that we have to increase the size of our data set, right? But you don't get patients you don't get patients that we can do this for that often. So, which is why right now in like in the neurosurgical community, like there are attempts to try to make like a database of like all these kinds of patients, so that people have like a large set they can work with. Yeah, it's kind of like this is basically like it's like if you learn statistics, right? You learn about like sample size, and this is basically like what we're touching on. Like sample size matters for when you're trying to design a model. Yeah, but like even so, I think we at least have a good start. We have a good start for gradient boosting techniques that for like making some kind of model. Yeah, I didn't touch on this. I didn't touch on this in the PowerPoint. I think I maybe I'll show this to anybody who's like interested. If they want to stay back, because we do have graphs of this, but there's a way to I guess convert like a regression problem into a classification problem by essentially saying that by putting some kind of classification like threshold, I guess. So let's say like you could say that like the model did well if if it predicts that a patient is going to have a value over a certain number when they actually do, and then the model didn't do so well if like it can't predict that. So if you do that, there's a way to like convert the regression problem into a classification problem, and we tried that in our analysis. Thought this talk would get a little bit long if I included that, so I didn't. So I didn't touch on it too much, but like again, if you guys want to stay back, I can show you. I can show you what we did with this as well. Yeah, and as I said in the last slide, we just have to collect bigger data sets and try comparing and compare more with other statistical methods. We've already done that, but we are going to keep doing that going forward. Yeah, this is a lot to take in. This is a lot to take in, and I think the important thing is just to remember is that like kind of machine learning is kind of a big field right now, and people really want to get into this a lot. And I'd say like especially going forward, like if you guys end up ever attempting machine learning, like actually you guys probably will, at least like you may once or twice. It's the topic is like such a big thing. There are some things I think that like really help for just like getting your like feet wet, I guess. And I think this is probably the most important one, is just to like learn more about like statistics. So like statistics is like it's like a pretty interesting field. I mean, even though it's definitely like scientific, but I think it's quite artistic in a way, because like this idea of like being able to see like the subtleties of like how your data set was collected or how your data set is like looks overall. So like these kinds of subtleties. So learning more about statistics is going to help, because in the end, like machine learning is just a large part of it is just applying statistics for designing computational algorithms. So learning more about statistics really helps. Yeah, so pay attention in your stats class if you ever take them, or if you have taken them. Yeah, go through them again. Yeah, and definitely it helps to just like get familiar with like the basics of just like coding. Actually, you guys are probably already caught up on that. Yeah, people are learning this kind of thing more and more going forward. Yeah. Yeah, just if you get familiar with coding, you're obviously going to learn more about the packages and statistical programs that are really good for this kind of machine learning project. Like R or MATLAB or Python. Yeah, and I think the most important thing is just not to get discouraged, because I basically like I said, it's like this summer, not last summer. Not yeah, whatever. Okay, so but the thing is like I learned this kind of thing during the summer, And, I had to like get caught up on a bit. Cause like, this wasn't something that I've like really tried before, but like, I was still able to like, do it at the end. Actually, we're taking this research over to a conference to present. So I think the important thing is just, to remember like, not to be discouraged. And like, even though there's like a lot to learn, like you don't have to like, you should try to know everything, but like, you don't necessarily have to in order to, do machine learning or apply it to whatever problem that you're currently working on. And, this applies even for like, if you're not doing medicine, right? If you're doing like science, like you're doing like physics or, chemistry, and you want to apply your machine learning, a machine learning paradigm for that kind of project, like it's, you just have to like, really know the basics, right? Because like I said, there are a lot of packages and a lot of programs that will just do it for you. So just, don't be discouraged and take it easy, basically. Yeah. Yeah. Yeah, that's pretty much all I had to say. Yeah, again, like this talk was just to kind of like show you an example of how machine learning is helping like help being used in a very specific field. In this case, neurological medicine. I think I see a question in the chat. Thanks. Thanks, Ryan. Yeah, but yeah, this was just like I said. The technical details of this are not so important. And again, like it's not like the tech, you have to know everything about the technicalities, because a lot of times you're going to be inputting data into a package and it'll spit it back for you, spit out the results for you. But the important thing is that you have to to know is that like machine learning is becoming a growing field, and like even in a field where I guess CS wasn't so big, like for example medicine, like you're starting to get like more and more attempts to do machine learning. Yeah, and especially given that like in a pandemic situation, right? Even if you can't go into a lab, you can still have a set of data on your computer, and you can still play with it, and you can still use your statistical packages and machine learning programs to try to make models. So it's definitely valuable to learn machine learning, and it's definitely becoming a big field going forward. Yeah, so this presentation was just to show you an example of that. All right. Yeah, that's pretty much all I had. Yeah, you guys can like stick around for questions and stuff. And again, like, I can show you guys a logistic regression output if you guys really wanted to see that.
I guess we can open up for like general Q&A first. Like, so just for context for high school students, you can ask things about the presentation or just in general about college or STEM stuff in general. I think it's a good opportunity for everyone.
I can ask a question, but it's more research oriented. So it seems like one of the big challenges with doing machine learning for medicine is that each patient has so much variation that if you train on data from other patients, then you might not exactly get results from what patient you're trying to test on, if that makes sense. So like how much, I guess specifically for the edema that you were working with, how much variation is there patient to patient? And is that why it made it easier to use machine learning in this scenario? Because
Yes.
maybe it's similar across a lot of different patients.
Yes, that's great question. Right. So again, like, your machine learning project is only going to be as good as like your overall like sample. So I think a really important thing is just to like take a general look at like the data and see what it looks like for each patient. So I remember like, cause we're predicting like the lactate pyruvate ratio, like in this case. So what we did was like for every single patient, we literally just like made like an Excel plot of like the lactate pyruvate ratio over time for like all the patients. And we just kind of like looked at each patient, and we saw that there was like a general pattern for like the patients. It was similar, it kind of like to how like there was like a general pattern for that multimodal monitoring diagram that I showed you at the very, very beginning. So it's definitely like what you said about variation is definitely true. And it's definitely a good idea to just check if there's like a general picture that like kind of like matches between like, your set. And if you want to capture like variations really, really well, like outliers, it's important to include at least a few patients that have that kind of like outlier inside of your data set. Because you're right. Otherwise, if you don't include that kind of thing, your model's not going to capture it.
Cool, makes sense. Thank you so much.
And then I'll get to Isaac's question in the chat. Oh, Ryan, you can like.
Right. So I actually had a quick question about like majors in that. So I'm currently planning on applying to in like some sort of like financial econ type of thing because I'm sorry, I was a little bit interested in like statistics or econ, but I'm not really sure if like majoring in like a statistics related field would like have an impact on like the type of work I'd be doing, especially
I think you cut
like,
off.
oh, I'm sorry. Is this better?
Well, the thing is like, no, I think like, yeah, no, I think like, because if you want to go into finance or economics, I think majoring in statistics field, or at least a field that's like dealing with a lot of numerical analyses, I think it is valuable. Actually, yeah, like because there are plenty of tech people, techers who have like majored, for example, in like math or physics, and they end up going to a lot of like finance companies like Goldman Sachs. And I think those companies tend to really value those kinds of people with that kind of background because they've done so much work with like looking at data sets and picking out trends and things like that. So yeah, I think if you were to major in like a field like statistics, I think it would help. I think it would help for if that's your end goal to get into like finance or economics or something like that.
Okay, I got it. Thank you so much.
Isaac, all right. What courses would you recommend taking in high school to prepare for medical research in college? Right. So definitely, I think a significant part of it is definitely understanding physiology and understanding how the human body works. So gaining a lot of like experience with like human biology, anatomy and physiology. So there are plenty of courses like that in colleges, and definitely you shoot for those if you can. Those will definitely give you like the most necessary background for like working with working in a clinical setting. Courses in biochemistry are also like super helpful. Yeah, especially like if you're working with like, for example, in this particular project, predicting like metabolites and like metabolite data, I think it would be helpful to know how those metabolites form. So biochemistry is definitely another helpful one. Yeah, and again, like I'm a chemistry major, so I'm going to be biased and say that like learning about chemistry is definitely like it's not going to hurt you, or like Gen Chem and like OChem. But yeah, I would say like pretty much boils down, like if I had to go with like three really important things, I think it boils down to those three. I think so, like human biology, and then like biochemistry, and then just like maybe like Gen Chem and OChem. Mm-hmm. Right, and if you like learn about human biology, like you're pretty much like gonna in some ways you're automatically going to learn about things like molecular bio, things like that. And I think the same thing applies for biochem as well. Yeah. Okay. Anybody else?
How did you kind of get this opportunity to work on like a machine learning project, especially if you I understand you're a chemistry major, and like how did you kind of get into this field?
Yeah,
if that makes sense.
Mm-hmm. So basically I got this data last summer. So when I say last summer, I mean like summer of 2019. I mean wait. Yeah, summer of 2019. Yeah, so I got this data set summer of 2019. Yeah, so I played around with it for a bit. Yeah, I think we really made progress after I brought in one of my co-mentors. Yeah, my co-mentor, Shane. His name is Shane, and he's an MD PhD candidate here at Caltech. Yeah, so he suggested the idea of just like trying this kind of machine learning or gradient boosting for this kind of procedure, for this kind of like problem. So I decided to go yeah, so I think that was basically my surf or my project this summer, summer of 2020. So science, it's definitely helpful to like talk with a lot of people, and like, you know, bounce off a lot of ideas back and forth with each other, because like you definitely get like, you know, inspiration from that kind of thing. Yeah, so just get to know a lot of people and really, yeah, and don't be afraid to like, you know, ask questions. I think like, well, what, you know, do you, if you, you know, ask them if, you know, if you have any ideas for this, or, you know, I was thinking about doing this, so what do you think about that? You know, so just, yeah, definitely be good at communication.
Cool. Thanks.
Cool. Anyone else? Well, all right. Yeah, I'll be like hanging around a bit. So like if anyone wants to like ask questions like in like privately, like I can, I'm hanging around for a bit, so you guys can do that if you want. But otherwise, yeah, I got nothing else.